loud. Okay. So is this full screen for everybody? Yes. Okay, good.
There's a slight delay.
All right. So today we're going to talk about the Bell inequality and the EPR paradox. Oh no, this is blocking the title. Okay, it's fine for you. Yes.
Yeah.
Okay. So let's see. What's wrong with quantum mechanics according to Einstein? Well, in classical physics, we study properties of objects that exist independent of observations. So, for example, the position of a tennis ball. You assume that the tennis ball always has a position, but you figure out what it is by measuring it, and it doesn't really disturb the object or anything. So in this setting, measurements simply reveal physical properties that were already there. In quantum mechanics, something strange happens. We deal with physical properties which are not determined until a measurement is made. So it would be like the tennis ball not having a position until we measure it. So enter EPR. So many physicists rejected this view of nature and about the quantum mechanical view of nature. And one of them was actually Albert Einstein. So he co-authored a paper with Nathan Rosen and Boris Podolsky, where they proposed a thought experiment that they believed would demonstrate that quantum mechanics was not a complete theory of nature. So what they did was they postulated a sufficient condition for what they call an element of reality, which is a certain physical property. And this is really a bad way of studying nature. So generally, when you study nature, you don't want to impose restrictions on nature. You want to kind of discover them. But they did it this way. So they postulated that it should be possible to predict with certainty that the value that an element of reality will have immediately before the measurement. So back to the tennis ball example, they postulated that it should be possible to predict what the position of the tennis ball is going to be right before you measure it. So things should be deterministic. But it turns out in quantum mechanics, that's not the way things are.
The quote from Einstein to Niels Bohr, God does not play dice, to which Niels Bohr replied, "Don't tell God what to do with his dice."
Okay, so let's just consider an example of what they were thinking. So take this entangled pair of qubits belonging to Alice and Bob, respectively, to be 0, 1, minus 1, 0 over root 2. And suppose Alice measures the spin along the v-axis. This is v dot sigma. Then she can predict with certainty what the result of Bob's measurement will be. So here's the proof. Suppose A and B are the eigenstates of v dot sigma. Then we can find complex numbers, alpha, beta, gamma, delta, where we can expand the 0 and the 1 to the computational basis in terms of these eigenstates. Now, if we substitute these expansions into the formula for psi, what we get is something that looks like alpha delta minus beta gamma times this state here, which is pretty similar to the original one, except 0 is now A and 1 is now B. And this is nice because A and B are the eigenstates of v dot sigma. So when we measure it, this wave function will collapse into either the AB or the BA states. So alpha delta minus beta gamma is actually just a phase factor here, because this is the determinant of a unitary matrix. It's the matrix alpha, beta, gamma, delta. But so since it's the determinant of a unitary matrix, it has the form e to the I theta. It's a phase factor. But quantum states don't care about global phase factors, so we might as well just throw this away. So anyway, we try to measure this, and we get either a +1, maybe that's the A eigenstate. And if that's the case, then the resulting state is this AB state here, which implies that Bob's qubit is in the state B, which would correspond to the other eigenvalue, which we call -1. On the other hand, if Alice gets the B state, then she measures the eigenvalue -1, while Bob will then be in the A eigenstate, which has eigenvalue +1. So no matter what the result of the measurement is, they measure opposite things, and more importantly, Alice immediately knows the result of Bob's measurement. So Alice can predict with certainty, just by measuring her qubit, what Bob's going to get when he measures. Okay, so nature says no to this. So nearly 30 years after the EPR paper, there was an experimental test. It was proposed that could be used to check whether or not the EPR pair or the EPR proposal was valid. And as it turns out, nature invalidates this view that Einstein and his co-authors came up with, and it agrees instead with quantum mechanics. So the key to this experiment is a result known as Bell's inequality. So here's the setup. So imagine we perform the following experiment. We have Charlie, who's a third party, and Charlie prepares two particles. I wrote TO. Okay, anyway, Charlie prepares two particles and then sends one to Alice and the other to Bob. Okay. After receiving her particle, Alice performs a measurement on it. And suppose that Alice has two choices of measurements she can make. One of them we'll call PQ, the other one we'll call PR. And she chooses which one to make at random. So she flips a coin or something, some other random procedure. So let's suppose that the measurement outcomes for either apparatus is just ±1, just for simplicity. Okay, so Bob performs the same experiment at the same time, but with the possible measurements PS and PT instead of PQ and PR. So two more measurement apparatuses. Apparati? Apparati. Oh, the book says apparatuses.
Well, it's a Latin word, so the pluralization is that way.
All right then. Which also, so these guys also have two possible outcomes, which are ±1. Okay, so let's first consider the picture that EPR came up with. So this PQ, PR, PS, and PT, these all have definite values. QR, S, and T, let's call them. Okay. So they're all ±1, but they have it
Assigned to them, maybe.
Yeah, they have it like assigned to them before we make the measurement. Okay. So we need to do a little algebra first. We're going to get an inequality out of this. So Q times S plus RS plus RT minus Q times T is equal to Q plus R times S plus R minus QT. So all I did was factor out an S and a T, right? So since R and Q are ±1, well, if R and Q are the same, so let's say they're both +1, then this term here, the R minus Q term is 0. And if they're both -1, the R minus Q term is 0. Meanwhile, the R plus Q term is either +2 or -2. If they're different, then we get the opposite. Q plus R will be 0, and then R minus Q will be either plus or -2. Okay, so yeah, so it follows either Q plus R or R minus Q is 0, and so multiplying by S or T doesn't have really any effect. So either way, we have that this quantity is equal to ±2, because well, when this is +1, then for example, this is +2 here, and then S takes the value ±1, and so the result is ±2. And you can do the same thing for all the other options. So this guy is always ±2. So let's let P of QRST be the probability that before the measurements are performed, so we're assuming this thing has definite values for all these random variables, the system is in a state where Q is Q, R is little r, S is little s, and T is little t. Then the mean value of QS plus RS plus RT minus QT is given by just ordinary probability theory. It tells us the mean value is the probability of measuring that outcome times the quantity we're taking the expectation value of. But this guy, we just said is always plus or minus 2, which means that it's always less than or equal to 2. And so what we get is that this whole thing is less than or equal to the sum of the probabilities times 2. But the sum of the probabilities is always 1. And so what we get is 2. And so that gives us, so by expanding out this, or sorry, distributing, I guess, this expectation value.
Which you can always do.
Yeah, the expectation is linear. We get this inequality. This is one example of a Bell inequality.
Isn't it, can't you like actually sandwich it to say like this quantity is less than or equal to 2, but also greater than or equal to -2? So it's really squeezed on both sides.
Yeah, you could. Yeah. So this guy here is always greater than or equal to -2. And so this is greater than or equal to the probability, or the sum of the probability times -2, which is just -2. So yeah, you could go both ways, indeed. Okay, so what does the quantum mechanical side say about this? So let's consider as an example the state psi equals 0, 1, minus 1, 0 over root 2 again. So Charlie prepares this state and he gives Alice the first qubit and he gives Bob the second qubit. So let's suppose that they perform the measurements of the following observables. So I just list them here. So Q is the measurement of the spin Z and the X direction, let's say. And then R is the spin X and the X direction. Wait.
Yeah, so spin Z should be in the spin in the Z direction.
The first particle, sorry.
Yeah, on the first particle. Oh,
yes,
I see what you're saying. Yeah,
sorry.
So the subscript also throughout quantum computing is always the space you're acting on.
Yeah,
right.
Yeah.
All
right, my bad. So Q is the measurement of the spin Z of the first particle. R is the measurement of the spin X of the first particle. And then S is a difference of spin Z and spin X. And then
the addition of spin Z and spin X.
Yeah, minus the addition, sure. Yeah. And then T is the difference. So you can show by computing the expectation values of these that they're all 1 over root 2, except for the last one here, which is minus 1 over root 2. But conveniently, this is the expectation value that we're subtracting, right? Remember, we considered operator, or I guess, I don't know what I call this, the quantity of this form, where this one has a minus sign. And when we do this, what quantum mechanics says is that the sum of these expectation values is equal to 2 times the square root of 2. But that means that Einstein, Podolsky, and Rosen, their view predicts that this quantity is less than or equal to 2, while quantum mechanics predicts that this thing is equal to 2 times the square root of 2. But wait, 2 root 2 is greater than 2.
On good days, yeah.
So what gives? Well, the two pictures contradict each other. And so one of them must be wrong. So when you perform this experiment, we're testing whether or not EPR was correct. And as it turns out, EPR were wrong, as the experimental evidence indicates. So what do we learn from this? Well, there were 2 assumptions that EPR made, which are questionable. The first one was the assumption of realism, which says that the physical properties PQ, PR, PS, and PT have definite values QR, S, and T, which exist independent of the observation. So back to the tennis ball example, the tennis ball having the position, a definite position before you measurement would be realism, which is something you're used to in classical mechanics. But when you talk about quantum mechanics, you observe things on a subatomic level. This notion of realism seems to disappear.
The collapse of the wave function in particular, right, is the antithesis of realism. Like, what does that even mean physically?
So the other assumption they made was locality. So they assume that Alice performing her measurement does not influence the result of Bob's measurement. So if locality were not true, this would break the principle of relativity, right? It would Einstein started with the assumption that the speed of light is constant in every reference frame, and information or interactions cannot
energy, information or energy, things like that, those can't travel. Technically speaking, there's nothing restricting interactions because those aren't physical.
So Alice measuring her qubit at the same time as Bob measuring his qubit. If that were to happen, then Alice measuring her qubit could not affect Bob's qubit because the information about Alice's qubit, her wave function collapsing, will not propagate to Bob in time, assuming the speed of light is obeyed. So together, these assumptions are known as the assumption of local realism. So the Bell inequality shows that our universe is not actually locally realistic. So one of these two assumptions must be false, or both. Yeah, it could be both, but at least one of them, which seems to go against our classical intuition. So that's always great.
That's a really stupid name, I just have to say. Our universe isn't realistic.
Yeah, I mean, obviously it is. Like, this is the real life.
Like, that's
It's
the
not
baseline.
Yeah, I think, I have a real issue with like the sort of in-message takeaway that Nielsen and Schwang says, which is just like, oh, there's something weird going on with these entangled particles, which I think is the smallest possible thing you could walk away with. And even just your comment that like that's a stupid name to call it realism if it's not real is a better comment than Nielsen and Schwang. Entangled particles are weird, but yeah, I guess can I chime in with a few modern perspectives that I happen to know about this?
Go for it.
All right, so people hate this, right? They hate how unreal quantum mechanics is, and that you seem to always have something that's lost. And so there's an approach there called like hidden variable theory, which Roy, you've been in Willie's class, you've probably heard, which is essentially like there's something there that we could know and that we don't. And that's determining how everything goes. So John, when he taught quantum computing, described it as invisible Russian gremlins traveling on your particles who beforehand have already decided what they're going to make sure that you measure. And using the Bell inequality and the Bell test, you can actually show that these invisible Russian gremlins, if they do exist, even they can't be non-local. Like if there is some parameter that's determining these things, they don't exist, or they don't exist locally. They have to be able to communicate faster than the speed of light. And testing for these invisible Russian gremlins is called the loophole-free Bell test. Basically making sure that your experiment is large enough that you literally cannot communicate with each other faster than you can take measurements. And recently-ish, I think past year or so, maybe a few more years than that, but definitely like this century, this decade.
I want to say Mark said 2015.
Yeah, this century, this century, this decade, which is cool. They've done loophole-free Bell tests. Yeah, I think, we had there was a guest speaker for the Hearn lecture talking about it. And that was done at NIST Boulder, I believe. And they just set them up at a big corner and they made sure they were far enough away. And so they've definitely tested it. And so far, those Russian gremlins, if they exist, cannot be local. And we like to believe that the universe is pretty real. So yeah.
One thing I want to say is that everybody likes to conclude from this that hidden variable theories can't exist. But actually, this is telling you that they can exist, but only if you drop the locality condition, which is not something that most physicists want to do because of relativity. But
yeah, the locality condition, I feel like, is very easily misinterpreted, because if you start with two entangled particles, so quantum field theory says you can have entanglement start from two things that are space-like separated, time-like separated, both. They can be very separated and causally separated and still be entangled with one another, but you can't transmit information from them. So you could do this potentially with entangled particles that never were close to each other. and you wouldn't be able to conclude anything until you came back together. So at some point, like your causal curve, if you will, has to intersect for you to be able to meaningfully transmit information about what's going on. Alice and Bob have to get together and compare results, which is also really cool because it seems to imply that information is physical. Like you can do the entanglement test and that's fine, but the actual information, the knowability, that's physical and that has to obey.
I've always felt that was true. But yeah, I really like this guy, Eric Verlin, who constructed a theory of gravity, which is like it emerges from a theory of information, which is so wild. But apparently, it gives you general relativity as an approximation. So I've heard. So,
how do you spell their name?
Eric Verlin. Let me try to look it up. I gotta try to look it up because I don't know.
Okay. But also, I just think that this is the cool, like, computational aspect of things, because I feel like the computer scientists always kind of deal with information technology, and they treated information as physical from the get-go, but physicists, I don't think, treat that as a very, like, physical quantity a lot of the time versus it is a physical thing.
So Eric Verlin, I like this guy because he challenges the notion of dark matter. He says, okay, well, what if instead of postulating the existence of something we can't see or seem to measure, what if we just try to fix gravity? And so that's what his theory of gravity attempts to do. And from what I can tell, people tend to criticize it pretty profusely. But I mean, they also criticized Einstein when the theory of relativity came out. But his results seem to indicate that it reproduces the results of Newton and Einstein, I think, as approximations, which is what you want.
What do people criticize about it?
I don't recall. I haven't read about it in a while.
I think, in general, dark matter is a pretty popular theory, which I know I get to critique because I'm not in astronomy, right? And I'm not in cosmology. So I get to think, yeah, it's kind of funny. Your theory is, I don't know. But the similar criticisms have been lodged at quantum physics, right? Because like Heisenberg uncertainty, like you build in uncertainty, right? You build in, you don't know. But I feel like the problem with Verlin's argument for a lot of people is that it goes against the larger accepted opinion, more or less, right?
Right. There could be some big, holes in his theory that haven't been worked out yet. I'm not positive. I haven't really read too much.
Just going against the grain shouldn't be bad as long as it's not like.
It has to be well motivated. So going against the grain isn't bad if it's well motivated, but if you're not very careful about your arguments, it can be a bit arbitrary.
I think the difference between Verlin and Einstein is that Einstein had testable predictions, and I don't think Verlin does yet.
I mean, even EPR turned it out to be testable, which is interesting because a lot of the intuition interpretation behind quantum mechanics is not testable, but that one was. So
he has a Twitter.
Follow Eric Verlin. That's going to be the homework for this.
Yeah, we all have to follow Eric Verlin.
You don't even have a Twitter.
Tell him he's supported by the Einstein enjoyers.
I think at one point Cole unmuted. Did you have something to say, Cole?
I was just wondering, is another name for the hidden variables you were talking about the spooky action at a distance?
No. Although, hi, it's Mary Catherine.
Hey, Mary Catherine.
Sorry, I'm back from the dead.
Welcome back. We missed you.
We really did.
But to answer Cole's question, though, the spooky action at a distance actually refers to entanglement in general. Mm-hmm. So then the whole property of entanglement. So the hidden variables are an attempt to kind of rationalize that in like a classical context. but it only works if you drop the assumption of locality. So that's something that physicists don't really want to do because of special relativity. So there lies the problem.
Okay, cool.
Yeah. I think spooky action at a distance was also a title of a John Dowling paper. So, you know,
Was it really?
I think something like that. Maybe had something to do with quantum internet or something like that. It is very.
I had a very attractive talk that I gave at Tulane called what was it? Teleportation, zombie cats, and spooky action at a distance.
Very nice. But yeah, this is just to clue in Mary Catherine, because she hopped in on the question portion. We were talking about the EPR paradox and just like making observations about what that implied for like physics in general, nature, and also quantum mechanics in specific.
I'm sad I missed it.
All right, I guess I'm gonna go through the whole thing again.
Honestly, you speed ran that.
I'm sorry. There was much to
Yeah,
it.
it's
It's like,
already done.
it's like 3 or 4 pages in the book. All right. Yeah.
Also, a quick question, especially since Mary Catherine is here. Is 5:30 a little bit easier for everyone than 5?
It doesn't make a difference to me personally. I don't know about everyone else on the time zones.
I
It
think
works
we're all
easier.
central. Oh no.
I'm Eastern, so
Oh,
it works
yeah.
better because I start dinner at 6. So maybe 6:30 would be or 5 o'clock your time, y'all's time.
Okay.
Wait, so you want it to be 5 or
5:30.
Yeah, 30 would be
30 minutes later,
fine.
which I
Okay.
think was the first meeting. But I'm just advocating for my girl because I miss her.
Thank you. Thank you.
Okay. Let's check out the schedule.
Stop recording.
Yes.
Okay.
Am I the only one that's been missing a lot? Because I haven't been here in a while.